What's up, scholars? Mr. Ipshin here. We're going to be starting unit number 4 today. That is on work, energy, and power. One of the lovely things about this unit is that most of it's not new, and I think conceptually speaking, students usually have a pretty easy time understanding things. So that's good news, and also in general, the math in this topic isn't too bad. We're going to get into a lot of that, but what I want to do today is just go through an overview of all three of the sort of different sections or topics, like broad topics here. So the first thing we need to talk about are systems. Systems are, as you can see what I wrote there, collections of objects, and objects have no internal structure. So let me give you a couple of examples of some systems. One example of a system might be a person, I'm going to draw this poorly, pushes a box. We've seen this already, with mass m, and let's say they just push it across the floor and it accelerates, as an example. Okay, here the objects would be the person, and we're going to assume they have no internal structure, which is a terrible approximation, but it makes the physics easy, and that's our goal. We're going to assume the box is made of no molecules. It's just like a Platonic ideal of box, and then you've got the floor, which is itself one single object as well. Another system that is internally very complicated might be something like a cup of coffee. Let's say a cup of coffee. Okay, let's have some steam coming off of that for effect. It looks like it's being electrified. Anyway, so let's say we've got a cup of coffee sitting on a table. Of course, that's made of like moles of water and coffee molecules, etc. I'm not a chemist. Anyway, so we can reduce that entire thing down to, if you've taken chemistry, like PV, and R, and T. In other words, what's the pressure, volume, temperature, and the number of moles of that thing. And you can do all kinds of types of interesting physics, but in reality we know that there are many, many, many molecules bumping and moving around and doing all kinds of crazy things. But the whole goal of physics is to simplify things by making a system. So we would say, I know this sounds kind of weird, but we would even say that coffee has no internal structure. It just has a few properties like, pressure, volume, the number of moles, gas constant. If you've taken chemistry, you recognize that. And then over here, we just have a few objects with no internal structure. So when we talk physics, we simplify things, and what we talk about is basically two kinds of systems. So we have open systems and we have closed systems. Now, in reality, everything, except for maybe if you consider the universe as a system, everything is an open system. Here's what an open system is. It's in an open system, energy is not conserved. It can be transferred to its surroundings. So, for example, in a simple physics problem, we might consider it to be frictionless and no air resistance and so on. But in reality, as you slide this box across the floor, it's going to heat up the floor, which transfers some of that kinetic energy to the floor. So over time, the person box system, with its whatever energy it starts with, it's going to lose some of that energy because it's an open system. Okay? That's true also of this cup of coffee. As it cools off, it's transferring some of its thermal energy into its environment. Now, a closed system, there really aren't any truly closed systems because things are touching, there's always heat exchanged, and so on. So let's give a definition of a closed system. So as I said, energy is completely conserved in a closed system. That would be sort of the idealized case. So I'll write that word here, ideal or idealized. So sometimes what we'll do is we'll assume that this is a closed system. We'll assume that no energy can go from the box to the floor. Or what we might do instead is treat this whole scenario like a closed system and ignore the outside world. So we might say, yes, we'll exchange energy between the box and the floor, but the total number of joules of energy, let's say we started with 100 joules at the beginning, it's going to be 100 joules at the end here, ignoring the rest of the world. So we can think of our system as sort of a picture or a box of whatever we're looking at. So in a closed system, which a lot of times in physics, to make things simple, we'll assume things are closed in an ideal fashion, even though we know that they aren't. So I wrote a bunch here for our next piece of information, critically important, so as I'm speaking you can be writing here, but the next term we need to understand is a physics term that has a sort of everyday application, but the term work in physics is simply how energy is transferred between objects or systems. So as an example, we can think of this system here being a person and a ball, and each object, so the person and the ball, those would be our two objects. Let me actually put a box here around our system. So here's our system, and this person is going to do work by lifting the ball, like I've got here. I'm lifting this ball, and I'm going to do positive work on that. And the whole idea is that I'm transferring energy from me to the ball. I have fewer joules of energy than I had just a moment ago because I had given them to this ball. Okay, I can't get that back, and then when I lower it, it's kind of lost to heat. Anyway, so the person does what we call positive work on the ball to transfer their chemical energy to gravitational potential energy. So that's exactly what I've just said. The important note here is the overall energy that the ball has increased. It had less potential energy down here than when it was raised up. And importantly, the person has less energy overall. So it's an even exchange here. We're assuming this is an ideal system. Let's say 10 joules of energy is expended by the person in terms of chemical energy. All 10 of those joules go into gravitational potential energy. Okay, next I've added sort of a more mathematical, or it lends itself to a more mathematical definition. So work is a force exerted through a displacement and in the direction of that displacement. So let me show you what I mean. Let's again go back to our box example. I'm going to not draw the person so the diagram is easier to understand. And let's say this time we're actually pulling on the box, and let's say we're exerting a force up at an angle like so. This is a pretty classic example of how to talk about work done. So what we're saying is we're going to pull this sled across the ground, and importantly we move it through a distance. I'm just going to use the letter D right now, or D for displacement, or in this case distance and displacement mean the same thing since we're not changing directions. Anyway, what's important here is that when we're doing work, when we're trying to transfer energy from whatever force, whoever's exerting this force or whatever's exerting this force, to, let's say, kinetic energy of this box, well, the only force that counts here is this force that's parallel to the motion. So sometimes we'll use this notation F, two lines there meaning parallel. So the work done here, according to that definition, is going to be as follows. Work is the force done in the direction of displacement, so F parallel, times D. Or if you look at the trigonometry here, this is the adjacent side, if we call this F parallel. So that would be the cosine. Okay, so W, work is the force times the displacement times cos theta. Really it's F cos theta times D, right? So this is F cos theta. We just move the cos theta to the end just for convenience there. So this, either one of those is really a good definition for work, and in fact both of those occur on your AP equation sheet. Alright, so the next quick topic we want to cover is mechanical energy. Mechanical energy is the sum of all kinetic and potential energies that an object might have. So we usually tend to represent, or I tend to represent mechanical energy with ME, and that's going to be a combination of an object's kinetic energy plus its potential energies, which we can write PE. Okay? We might change up notation as we go along, but this is for simplicity here. Now, kinetic energy can take several forms, but for right now, we're just going to talk about sort of standard kinetic energy, and the equation for that is 1/2 times the mass of the thing times its speed squared. And then there are several types of potential energy. So this is kinetic energy. So there are several types of potential energy. One of them is called GPE, for gravitational potential energy, and that is mg delta y, or you can, I tend to see this more written as mgh. So we can think of gravitational potential energy as the energy of position in a gravitational field. So what I mean to say, and we'll talk more about this, is that this has more potential energy as I increase the height. And it has more potential energy in a stronger gravitational field, and the heavier, the more mass it has, the more gravitational potential energy is. So these are the same. Sometimes you'll see it written as change in y position or just the height. We'll talk more about that. And then there are a few other forms of potential energy. We're going to write these down just for fun, but we're not going to stress about the definition. So there's also elastic potential energy. Elastic potential. That would be like in a spring or something like that. Just for fun, we would write that something like this. I don't know. Elastic potential. It ends up being 1/2 times how strong the spring is times the displacement of the springs squared. You can ignore that for right now. We don't care too much about that. And the other type of kinetic energy that I wanted to mention is thermal energy. Now, we don't really have an equation definition of that at this time, but what that is the average kinetic energy of molecules in a system. So the thermal energy is sort of like heat energy in a system. So when I rub my hands together, I increase the thermal energy in my hands. And next, we have the conservation of energy. So energy conservation. Energy conservation says that energy can be neither created nor destroyed, but instead transferred between. So for our purposes, energy conservation, we can write it in the way you've probably heard before. Energy can neither be created nor destroyed, but instead can be transferred between systems. So the basic idea there is however much mechanical energy, that's what we're going to focus on here, you start with, that's how much mechanical energy you're going to end with. Now we'll introduce some things like what happens when there's friction, where does that energy go? But we won't worry about that right now. What that means is the total kinetic and gravitational potential before an interaction is going to be equal to their sum after the interaction. More on this to come, more practice for later, but that's it for today. Thanks so much.